Hello everyone, I am Revanth and today I'll be presenting my computational photography project in which I implemented the paper Laser Speckle Photography for Surface Tampering Detection. This paper presents a novel method to detect surface tampering which has valuable applications in forensics and security. Here you can see two images of a wall before and after it has been touched by the hand. As you can see, just by looking at these two images, we cannot determine whether someone has touched the wall or not. The paper uses a technique called laser speckle imaging to address this issue. I'll first give an overview about laser speckle photography. When a coherent laser light illuminates a surface, this is a surface, each tiny point on the surface acts as a secondary light source. And this secondary light source uh, sends us back the reflected light waves. And these light waves interfere with each other and form a constructive and destructive pattern. And what's interesting here is even a slight deformation of the surface or even a slight pressure on the surface can change the position of these tiny points, which which can move the points away or towards the camera. So here you can see this is a tiny point, and when you touch the surface this point moves away from the camera, and this can create an entirely new interference pattern. In this method we'll use an SLR camera and a laser projector. To implement this technique, we first capture a before image of the scene illuminated by the laser projector before the tampering. We call this image a reference image. We later take another image of the scene, which we call the target image, and then we compare the reference and target images to compute the similarity map. This similarity map gives us the information about tampering. After each capture, we extract the luminance channel of the image. This is because most of the intensity variations in the interference pattern can be observed from the luminance channel alone. And we don't get much information from the chrominance channels. So to improve the computational time significantly, we can use just the luminance channel. So here we have a reference image and the target image, and we have extracted the luminance channel from both of these images. Once we get these, we need to do image alignment. This is because the laser speckle imaging technique is highly sensitive to the position of the camera. So to perform image alignment, we take the reference image, we randomly sample small patches from the reference image, and then do template matching to find the corresponding patch locations in the target image. Using these correspondences, we can compute homography matrix. And using this homography matrix, we can warp the target image to match the reference image viewpoint. Once we align the images, we can estimate the similarity map. We do this by taking both the images, and we take each pixel from both the image and take a small patch around these pixels and compute normalized cross correlation. This the value of this normalized cross correlation gives us a similarity map. This tells us how similar the patches taken from these two images are. Lower values indicate tampering around the pixel. Now I will show you some of my results. So for the first thing, I chose a carpet surface at my home. This is the reference image captured before tampering the surface, and then I walked over the surface and then took the target image, and using the process I described above, I computed the similarity map. So in the similarity map, in this laser projected area, you can see my footprints clearly. Similarly, with my hand, I just traced out the course number 15663 with my bare hand on the wall, and visually from the image, from the captured image, you cannot see it, but from the similarity map, you can see the digits clearly. One thing to note here is the contrast of the speckle pattern is dependent on the aperture of the camera. The smaller aperture, which is the first image here, gives us better contrast, while the lower aperture has less, while the larger aperture has less contrast. This is because larger aperture actually averages out the speckle patterns, thereby blurring the contrast. I conducted another experiment where I fixed the projector position here. So in the cases where you cannot move the projector, we can use this technique. So we'll just place the projector somewhere, and we'll project the light. We'll project the light to a highly reflective surface. We can use a mirror, but for my experiment, I just used my mobile screen. So the laser projector projects the light to the a reflective surface, and we can redirect the light to a wall, for example, and the camera captures the image of the wall before and after the tampering, and you can similarly estimate the similarity map. So here you can see this is the captured image of the wall, and then luminance channel of the wall, and then this is my handprint, you can see clearly. This technique also has limitations. It performs poorly with transparent surfaces. Here you can see I captured two different transparent objects. One is a water bottle and the other is a filter. Um, and the results, I touched both the objects with my hand, and I cannot see fingerprints here in the similarity map. So the reason behind this is, in case of transparent surfaces, most of the light undergoes internal reflections, and very small amount of light undergoes surface scattering. Since laser speckle imaging relies on surface scattering, it cannot. It's extremely like hard to recognize the um, surface scattering here. And yeah, thanks for listening.